That he should be here in time to hear the beginning of this talk.
I think he should, yeah.
And so I think there he is.
Okay, without any further ado, we'll go straight to the next talk, which is Lou Kauffman about Iterant Algebra.
Okay, thank you. Does somebody have a laser pointer right here? Yeah. Oh, good. Oh, is that one of those things that actually controls the...
You put
let's try it.
Incidentally, does anybody remember Peter Marcer as a member of ANPA?
Yes.
Yes.
He's just on Skype to me now, so we can
He's
say
trying to
hello
call.
to him.
Hi, Peter.
Wait, I'm gonna call him back in. Hello.
Okay, so I'll start. The optical illusion that I have on the slide doesn't have very much to do with the talk. It's just a favorite illusion of mine. But it probably has a lot to do with thinking about reality in as much as there isn't any triangle around the middle. It's entirely approachable, but you see it anyway quite clearly. I always thought that was fascinating, and maybe somebody has a comment about that, but later for comments on that. Oh, just a minute. All right. So I'm going to talk about what I call iterant algebra, but I'm going to begin by making some remarks about Majorana fermions and braiding, because this will later be modeled by that algebra, and this is a nice place to start, and we'll come back to it. So you may recall that for a standard fermion, you have an annihilation operator and a creation operator, and maybe I have put them in the right order for once. And they correspond to the fact that the antiparticle is distinct from the particle. You have F star and F, and you have that F squared and F star squared are 0. But F star plus F star F is equal to the identity. I'm not motivating these here, but the first one has to do with the Pauli exclusion principle, and the second one is the analog for fermions of the usual commutator relationship for bosons. But anyway, that's an interesting bit of algebra, non-commutative algebra. And on the other hand, here's another bit of algebra. And this is the kind of algebra I'm going to be talking about as I go in. And that is a little Clifford algebra. So I remind you that Clifford algebra, you can think of a Clifford algebra as being generated by elements whose squares are 1 and that anti-commute with one another, which is, if I get this pointer correct. It's very light. I see. Okay. And I commute with one another and their squares are 1. Right? That's an example of a Clifford algebra. Rather than define Clifford algebra in some general sense, I'll just say that a Clifford algebra is an algebra that has a basis such that the squares of the basis elements are 1 and they anti-commute with one another. Okay. And then the interesting thing about the fermion algebra is the following. That you can make these nilpotent elements by taking A plus IB over 2, where A and B are those Clifford algebra elements, and you can get the dual one, conjugate one, by taking A minus IB over 2. And this is just a little bit of elementary algebra. Notice that 4 times U squared, for example, just getting rid of the 2's, is A plus IB times A plus IB. That's A squared minus B squared, because I squared is minus 1. The assumption being that I is commuting with everybody, and A, B, and BA add up to 0, so everything adds up to 0. So you make this nilpotent element U, in this case, by building it out of Clifford algebra in the background like that, and then you will notice what happens to U star plus U star U, because if you take U plus U star and you square it, why then you see that you get U squared and you get U star squared, but they're gone, and then you get U star plus U star U. So you get U plus U star squared, and U plus U star That's just A. And so A squared is equal to 1. So you see that you can build the fermion operator in terms of this little Clifford algebra. And this all by itself leads to an untoward speculation which has recently been partially verified, that fermions ought to be composed of some other particles which have to do with the little Clifford algebra into which it can be decomposed. And those are often called Majorana fermions or Majorana operators. But if you believe that there's a pair of particles underneath an electron, then this equation would be a reality, and there are some evidence to that effect. So that's the little algebraic story that I have told before, and I wanted to tell again at the beginning of this talk. Yeah.
The TO there should
Just
have
a
been
moment. Yeah.
TWO, shouldn't it?
Sorry.
The word before Majorana.
Thus, mathematically, an electron is composed of, TWO, of course. Yes. Yeah, thank you. Right. Okay. So now I want to talk about the algebra in back that I'm thinking about. And so I'm going farther back. I'm thinking about recursion in the most general sense. And if I think about recursion in the most general sense, then it's back up in ordinary language. So for example, there's recursion in a statement like, I am the one who says I. Although you don't see it recursing, you don't see it going over and over again, because it just fits into itself. I am the one who says I. If I said the lamp is the one who says the lamp, or the lamp is the one who says I, none of those are fitting together. But the two I's and the two slots in that fit together and give a statement which we regard as fitting, right? And so I is a fixed point for the operator, the one who says. And so I can think of fixed points of operators. And fixed points of operators are sometimes things that just fit, and they're sometimes things that are the result of a continued recursion. So for example, if we're looking at the eigenvalue of a Hermitian matrix, then in some sense it just fits, in that you go ahead and solve and find an eigenvector, and then that matrix applied to the vector is equal to lambda times that vector, so it just fits. On the other hand, you may approach it by some limiting process or some recursion. It all depends on how you're looking at it. So I'm going around and around on this one a little bit before I go further. But the sign in the middle here is Wheeler's well-known universe, which is observing itself. And I don't know if Wheeler had any notion that this could be thought of recursively. He's thinking that an observation takes place in the quantum world of the universe at some apparently later stage in the development of the universe after the Big Bang, when the universe is capable of making an observation. And then the universe becomes actual because of the observation. So that's a quantum paradox, right? Because how could the universe have been actual before it was observed if you're thinking in terms of quantum theory? On the other hand, you can think of it as, at that point of observation, it comes to fit, just as it does whenever you make a quantum observation. The other is a sign for something which is re-entering itself. And in particular, I'm thinking of the whole range of either fitting as a solution or being produced recursively. So if, for example, you think of the operation here of operating on something by putting a box around it, for the sake of this slide, that's the operation. And then I'm looking for a solution or a fixed point to L is equal to putting a box around L. Well, if you think of it spatially as an infinite extent I guess this pointer is, yeah, you can see it if I find the place where I want to aim it. And this is supposed to be an essentially infinite nest of boxes, so if I put one more around it, it doesn't change it. So then it's a solution. But that solution is one that you can think of as having been obtained by a recursive sequence of events like this in time, getting closer and closer to the end result. So this brings up a number of issues which are interesting to think about, not the least of which is the relationship between time in mathematics and time in our actual experience. If you think about time in mathematics, it turns into things like sequences. A sub n is equal to n boxes in a nest. And there isn't any time at all. So time in mathematics is always gone. It's some structural model involving the integers or involving the real numbers with some index. But there isn't anything happening temporally in the model. It's structural. What happens temporally happens out here with a gesture, with a movement, with a clock, with a pendulum, and isn't something that I can completely capture mathematically. So that means that thinking about time in relation to mathematics is, in principle, some sort of incomplete process, no matter what you do. You're always going to miss. But you might get a little more if you had some insight that was a little different from someone else's insight. So there might be a crack in quantum mechanics that has to do with time. Or there might be a crack in the way you think about other temporal processes if you could find some better insight into the way time is working. And so it's worth looking at time in that regard. Of course, there are larger questions that are called the problem of time with respect to one thing or another, like the problem of time in gravity and so on. But I say there's just the problem of time, and it's interesting and important to think about that. And anything that I say about time from here on out in this talk is also going to miss. But nevertheless, I'm trying to think about it. So I'm thinking about the square root of minus 1 to begin with. What?
Lou, I just want to ask.
Oh, sorry.
What's incomplete? When you say
The mathematical model and what it models do never match.
Yeah.
I can talk about, I can make mathematical model, a differential equation, a discrete recursion,
Yeah.
but it's always a structure. It's a structure which is defined out of time in order to be mathematical. And there is, on the other hand, a sense in which it has something incomplete about it, even as a mathematical structure, if the recursion has some depth. Like if I said to you the nth prime, well, then you don't know what the nth prime is beyond a certain point. So the process itself requires doing the process in order to come to that. And you know how to do, but you know how to do the process in the abstract. If, on the other hand, I say the pendulum is swinging, well, I don't know how to model that the pendulum is swinging. I know how to model the swinging of the pendulum, right? And if I want something to happen, it has to happen. I can't model the happening.
Okay. Is completeness something which we desire?
Design?
What desire?
Desire.
Are we aiming for completeness in our system?
Oh, I didn't say you were necessarily aiming for completeness any more than I necessarily aim for completeness even in a mathematical situation. Do I really want a complete invariant of this manifold, or do I want to get some information about it? Right? I may not worry about completeness, or I may worry about completeness.
All right.
And then the incompleteness I'm pointing to is not quite the same as the mathematical incompleteness, right? Mathematical incompleteness says, here's this system, and there are theorems that are expressible in this system that it can't prove. All right, but here's this system, and here's things that happen in the world, and this system mismatches between what it can really say about them and what happens in the world. That's a different kind of incompleteness. Yeah.
Luke, I'm wondering, why is there trouble? What you seem to be doing is using the discrete domain to try and talk about something that's from every sense we have, not discrete. You know?
That's right. That's what I'm saying. And mathematics is couched in a language which is fundamentally discrete because it's fundamentally linguistic.
As well.
Yeah.
For instance, a differential equation, though you need to do a bit more algebra to generalize the equation so that dimensionality doesn't get you and anything like that. But the idea that you state that there is some change of a thing which occurs progressively with the element of a differential equation. If you take on board, to do it, you have to step outside of the discrete world that we live in at the moment. But when you do, I can't see that you're missing.
Well, I step outside the written world. I step outside the world that's expressed just in terms of symbols and language.
Except this is still in symbols
Yes.
and language.
I step outside that into making something.
Does that answer my
I step outside that into allowing some process.
We just have to extend our language so that continuity is part of it, and then we have the stuff we need.
Well,
so one
the stepping outside, I mean, I appreciate that the stepping outside is, to some extent, something that you might feel you actually do. But let's look at it again. I mean, I have a theory of knots and symbols for them, right? And then I have this piece of rope, right? And I have to admit to you that my theory of the knots topologically is good enough so that I feel that this rope should be allowed to be in and of itself a symbol for a knot. That is, I make the knot this way, and it's as good as having written it on the board, right? And then there are things I can do with this physically in the world, right? Like tie it up a bit and tie it up a bit more and so on and so on. And then I can put it into a physical process, like putting a force on it from here to there and find out that it all unwound, right? And there are all those things. A lot of them are out beyond my ability to model at the moment, but I can try to model them. There's geometry there.
Yeah.
But there isn't, but this is not using very much that's temporal. These geometrical things, I have the feeling that I could get more and more
aren't we able,
quite directly.
all of that
But if I look at this rope and let it swing back and forth, and it's swinging back and forth in time here.
Look, it seems to me that where our dimensionality of our space comes from, I like to refer to it as Carpenter space. It's got three dimensions that the Carpenter knows he applies to a box, otherwise it's not a box. And he's got a watch, if you can modern Carpenter. And
so you subscribe to four-dimensional space-time on block.
Yes. Because
well, that's a model.
Indeed.
That's a model.
But the point is that the relationships in it now do embrace the relationship with the temporal one with the...
I mean, you could hope that you will model everything, right? And there's a very eloquent passage in Wheeler, which I should read at this point, but I don't have it on my slideshow, in which he talks about, space-time on block, and we can write down all the equations. Let's write them down. Let's write down everything we know on the floor of the room and back out of the room. And then once we've written everything we know and we stand outside the room and it's all written on the floor, and I'm just sort of half quoting him, and then say fly. And this contains all the information about the universe, but it doesn't fly. But the universe flies. That's his way of, I quoted his poem, sort of half quoted it, but that's his way of expressing the same problem.
I can't see where the authority for fly comes from. Why?
All I'm saying is that, in your experience, time goes on, but in your mathematics, time does not go on.
Oh, yes, well, I was not worried about the mathematics, I was worried about the carpenter. What's wrong with the carpenters? They know about this.
Carpenters?
A carpenter has a tri-square which he makes wooden boxes true
Yeah.
wooden boxes with, and he has a watch, and he knows when he's got to deliver it by.
Yeah, I agree. I mean, so we know how to do things. The carpenter knows how to.
Well, our language comes from what we
He knows how to do things, so he does know how to handle things happening in time, but not everything happens by his pure will, and what doesn't happen by his will is beyond his model.
Well, true, but a decent carpenter's got that
So
abstraction.
are we arguing about anything?
Well, because I
I'm
can't
only
see why
saying
time
in a
gets caught on
qualitative
its own
way,
like that.
what? Now you wish to talk at the same time as I do.
No, I was just answering your point, that you don't seem to be focusing anymore, but it seems to me that separation of time like that, it's a mathematical claim, not an existential claim.
But that's all I'm saying, that mathematics, qua mathematics, as expressed, as shared, is a linguistic, discrete situation. It's worth recognizing that, and seeing that it never quite manages to model certain intuitions that you have, or maybe you don't mind. But mathematics is discrete by the get-go. So when it comes to talking about continuous things, you have the same problem. It isn't just time. Continuity isn't well modeled by mathematics. You have to go through wonderful logical gyrations to get to the real numbers.
Well, except again, the carpenter knows it pretty well. He's got a basis for it.
Well, the carpenter is working in the interface. I'm talking about the distinction between the mathematics and what you do. So what you do, other than write on paper or think with your mind, which the carpenter does, is on the other side.
All right,
So we could talk about this for a long time because the boundary, that's all I'm illustrating, is that the boundary is tricky, right?
all right.
Right.
Okay, thank you.
That's all I'm saying. And now I'm going over to a particular thing that I want to think about, which I've said before, but some of this I hope I haven't said before. So I'm looking to solve G equals G cross, but I'm looking to solve I equals minus 1 over I. And the transformation T of X is minus 1 over X is the one I'm looking for a fixed point for here, right? If X equals minus 1 over X, then X squared equals minus 1, right? And you could think of the transformation involved as T of X is minus 1 over X. And so if you put in a 1, you get minus 1, and if you put in a minus 1, you get 1, and it oscillates. And of course it will oscillate. If you put in 2, it'll give you minus 1 over 2, and then it will give you plus 2, and so on. It will oscillate. Whatever you put in there, if it's real, because there isn't any real number whose square is minus 1. So I'm looking at this particular behavior, and the behavior is one that you could imagine happening physically, or you could imagine happening mathematically. So if we go back and forth, right? And you can look at the behavior as being located in the interval that goes from plus to minus, or the interval that goes from minus to plus. Two ways of looking at that. And then I would like out of that to make the square root of minus 1 happen. And how are we going to do that? Well, you know my answer, but I'm trying to go slowly. So the way I'm going to do that is by adding an operator here. And that operator is keeping track of time in a certain sense. That is to say, the operator has the property that if you conjugate it by the operator, or if you move the operator past one temporal view of this, you get the other temporal view of it. So that the operator has the property that when you're looking at this in this time frame, and you shifted the operator past, it ends it up in the other time frame. It does one time step or one time delay on this way of looking at it. So it's as though I modeled, by putting a bit of algebra in here, one tick of time. One tick of time corresponds to shifting back a across the operator. And in this case, time ticking twice brings you back to where you were because it's periodic. So the square of the operator is 1. And then if you look at what happened to the +1, -1, the bit of algebra models a certain intuition. But I want to try to say the intuition and then go back to the model. The intuition is that, that this +-1 is buzzing, plus minus, plus minus, plus minus, in some temporal world that I can't quite capture. And when you try to combine it with itself, it takes a moment of time for it to combine. And so it ends up combining not plus to minus and not plus to plus and minus to minus, but plus to minus and minus to plus. And that means that you get minus, minus. And so you get -1. So that the -1, when you multiply this buzzing thing by itself, comes about because there's a little time shift there's a little time shift in the act of combining. A little time shift in the act of combining. And of course it has to be precise, which is where the algebra comes in. And I wouldn't know if I could make this actually happen physically if I tried to put two oscillators together and make them combine. They might not quite perfectly time shift, but I'm making a mathematical model. And in the mathematical model, the eta does the job. You see what eta did, right? Eta slid across here, changes the minus plus to a plus minus. They combine to give you minus minus, and the eta squared is 1, and so you get -1. So you get the model of the square root of -1 in terms of a little temporal action on the part of I interacting with itself. Now, the model belies itself. It's a good example of making a model which has a certain kind of insight in it, but it doesn't really model anything physically, and yet on the other hand, it feels like it models something about my intuition about how this buzzing thing is combining with itself to produce -1. All right? And the algebra works nicely. So we're going to take the algebra as a way of making the square root of -1. And what did we get out of doing that? Well, we got the following algebra, really. We got an E, which is 1 minus 1, an algebraic thing whose square is 1. You multiply it coordinate-wise, right? You just put them together like this with no twist. So there's two ways of putting together one of those waveforms. One of them is like this with no twist, thumb to thumb and finger to finger, 1 to 1 and -1 to -1. And the other way is putting them together with a twist, and then you get -1 instead of +1. And the eta is the twist, and the absence of the eta is no twist at all. And so I have the E, which squares to 1. And I have the eta, which squares to 1 for a different reason, right? It squares to 1 because it's a twist, and when you do it twice, you're back where you started. So it's a meta operator, which has been put back into the algebra at the same level as the rest of the algebra. And then we have that eta E is minus, E eta is minus eta E. That's what I said before. And maybe it ought to be emphasized. What's E eta? E eta is equal to plus minus and then eta, and that's equal to eta times minus plus, but that's equal to eta times minus plus minus. I mean, E has the property that when you take the negation of E, it comes back, right? I mean, the negation of minus plus is plus minus. So this is minus eta times plus minus. So that's saying that's equal to minus eta E. Sorry if I am belaboring the point, but that's what happened, right? So saying it abstractly, we have a little Clifford algebra. So what we find, and then we have that the model has the property that E eta, the product of the two Clifford elements, has square minus 1. And if we were just doing Clifford algebra, and we weren't doing all this underlying stuff that I was just telling you about, well, that would happen too, right? E eta multiplied by E eta is equal to E times minus E eta times eta, because eta E is minus E eta. And then what's left here? A minus 1, and E squared is 1, and eta squared is 1, so you get minus 1. So another shorter story would have been back when I was just talking about the abstract Clifford algebra for the Majorana fermion, to refer to that physics, would have been to say, well, we had these two guys, A and B, and they squared to 1 and they anti-commuted. If you take the product of A and B, you get somebody who squares minus 1. So Clifford algebra gives rise to a square root of minus 1 automatically, but I'm taking the story in a different way in terms of the recursion. So you see that you can think about the square root of minus 1 as a kind of buzzing entity that's plus and 1, plus or 1, minus 1, which is it, and it has the property that when you multiply it by itself, it rectifies and becomes minus 1. But then it generates a Clifford algebra. So the Clifford algebra comes out of nothing like that. It comes out of the recursion that's trying to generate the square root of minus 1. It comes out of the paradoxical plus minus that is involved in the recursion to begin with. So that's the basic observation, that you can think of this as a source of the Clifford algebra. You can think of trying to think about time as leading in this particular way to a Clifford algebra. And Clifford algebras have other interpretations, of course, like the one I started with. But this is an interesting way to think about how a Clifford algebra arises. And I want to keep thinking about it this way, even though there are other ways to think about it. By the same token, I want to keep thinking about the square root of minus 1 this way, as a kind of a plus minus, even though there are other ways to think about it. Now, we know that the square root of minus 1 can be thought of ever since Gauss and Argon. And I remind you, just for the contrast, right, that you know that you have this beautiful picture, which comes from around 1800, of putting I here and minus I here, and no thought of temporality, right? No thought of temporality, but that I is now interpreted as rotation by 90 degrees. And not only is it interpreted, but it works perfectly as rotation by 90 degrees. That is to say, I could take some triangle here, A, B, right triangle, and regard this as A plus IB, right? A this way, IB that way, and ask what happens when I multiply that by I. And what happens when I multiply that by I is that it becomes I hope you don't mind. I just find it interesting every time to write it down, even though everybody knows this. Right? You multiply I times A plus IB and you get minus B plus IA. And minus B plus IA means that you here have minus B and here you have A. And so here's the right triangle again with the angles, the corresponding angles. So this angle and this angle are now here, and they were here, right? Whoops, I got them wrong. There, that's right. We just turned that like that. So it did turn by 90 degrees. It actually turned an arbitrary vector by 90 degrees. This angle is 90 degrees. So it wasn't just that it was a diagrammatic thing. They really discovered, Gauss and Argon, that the whole, or at least Gauss probably is the one who understood this and the rest, that the whole thing becomes geometrical and that I is understood as an element that does a rotation in space, and then multiplying complex numbers corresponds to rotations in general. So the whole thing is this very strong geometric interpretation, and the fact that it also has a temporal and Clifford algebraic interpretation is just as important somehow, but is taken on a different frame and is not always thought about. People who do Clifford algebras, of course, are well aware of this, but they may not be thinking of it as I'm thinking about it, as having as strong a meaning as this one. This one is really very dominant, and for good reason, right? So that's interesting. And then I have a digression here that I couldn't resist telling you about. I met and, let me see if I can remember her name. No. It'll come to me in a moment. But a woman who wrote a book on cosmology, and her name will come to me in a moment. And she covered everything in great detail and talked about the history of things. And so she had to at some point talk about the square root of -1. And she says in her book, John Wallis, mathematician in Oxford in 1670, was the first person to interpret the square root of -1 geometrically. How many of you knew that? We usually say Gauss and Argon, as I just did. You can look it up on the Wikipedia and you'll find it's documented there. How did he do that? How did he do that? I just thought I'd digress on this for a moment. How did he do that? Well, he said, and he wrote this up in his book on algebra, apparently. He said, I know the following from basic geometry, that if I have a right triangle, and I drop the perpendicular here, and I call this distance, let's say A, and this distance B, and this height H, then H is to A as A is to H, sorry. A is to H. A is to H as H is to B, because these are similar triangles. Right? That's quite clear, right? A is to H as H is to B. This angle here is equal to that angle there. Similar triangles. So that says that H is equal to the square root of AB. Right? A basic theorem about right triangles, geometry. Then he said, but I am an aficionado of the, at that time, relatively new notion of negative numbers. So we have an origin here, and let's say we have +1 here, and we have -1 there, and let us put a right triangle here. Sorry, that's not very well drawn. Then this would be a line H here, a distance above the origin, right? And I shall regard this the A as -1 and the B as +1, and therefore H is equal to the square root of -1 times +1 equals the square root of -1. So therefore, I shall interpret the point at the point above the origin at unit distance from the origin as the square root of -1. He did that in 1670, and it didn't catch on, and then it got lost.
The idea of an origin was really even the idea of an origin was really quite new.
Partly because negative numbers were relatively new. I mean, I don't know. I mean, 1670, but if you go back to 1570, people were not so happy with negative numbers, so relatively new. And so he derives the square root of -1 in that way. Worth thinking about. And it's still in the realm of geometry. We haven't made it temporal over there.
Very interesting.
So,
John Wallace, I should write his name. In case you know a little bit more. Very famous mathematician. You know him. You know him for other things like Wallace's formula for Wallace's product formula for pi and many other things. But one of the first-grade Oxford mathematicians. Anyway, let's go on. That's what I just said. That little Clifford algebra is sometimes called the split quaternions. Why? Because if you were to take another copy of I that commuted with everybody and multiply some of those I and E, if you multiply E by I and Eta by I and put them in the right order, you have the quaternions. So it's sometimes called the split quaternions. Now what we've been doing is actually matrix algebra. So we just reinvented matrix algebra. And one way to see that, it's probably better if I do it on the board.
Are you saying that there's different roles of I in split algebra?
I'm sorry, the scrapping in the paper obscure what you said.
I was just asking, are there, is I playing two different roles in the split algebra? I mean, like one doing a shift and one.
Yeah. In order to go from quaternions from the split, from the little Clifford algebra over to the quaternions, the usual way to do that is to say, I will reach into this box over here and pull out an I that commutes with everybody that's different from the I just constructed. Right? And then you would have, let's try it out. I probably will get them in the wrong order or something, but let's take I, E, I, Eta, and E, Eta, right? Obviously I wanted Eta E here. Now let's try it. So let's multiply this by this and see what I get, right? Now I commutes. I commutes. So now do a little theme here. IE times I eta is minus E eta, and that's eta E. So I have this times this is equal to that. Now try this one. I eta times IE. Eta squared is 1, so I get IE. So this times this is equal to this. And lastly, eta E times IE is eta I, because the E squared goes away. But I commutes, so that's the same as I eta. So we got them to go around in a cycle as we wanted them to, and they each square to minus 1. This one because it does, and these by having forced them to do so. So this is the quaternions. So one way to go, so that's another notion. I mean, these are sort of hierarchy notions, right? How quickly can you construct a significant structure from almost nothing? But I didn't really try to start with nothing. But I started with something very simple, and I get to split quaternions quickly. And then I make this jump and grab an I from some box somewhere. That seems like too fast, maybe, but I don't have another way to do it. Actually, I do have another way to do it, so let's talk about that for a moment. It's not the same as this.
Yeah.
Let me show you the other way I know how to do that, how to get to the quaternions, right? Suppose we start with A, B, and C, Clifford, Majorana, okay? So that means that A squared equals B squared equals C squared equals 1, and AB equals minus BA, and AC equals minus CA, and BC equals minus CD. A little Clifford algebra with three guys. Okay. Now you know that if you take the product of the two Clifford elements, you get a square root of minus 1, right? So now we're in good shape. What we're going to do is we're going to say I is equal to BA, J is equal to CD, and K is equal to AC. And then you can check, you can do the exercise in your head. But that's true, so we have the quaternions. You believe me? I'll try IJ. Something went wrong. No. Just try IJ equals K for one thing to do. So then you would have I, J equals B, A, C, B, which is equal to minus the B. I'd like to get the B's to communicate with one another, but that means I have to hop this B over C, that changes the sign. Now I have to hop it over A and it changes the sign again, so plus. So that's this equal to plus AC, which is equal to K. Okay. So if you play with it, it all works. So here we created the quaternions without having an extra square root of minus 1 being forced on us by using an extra dimension of algebra. Yeah.
I just want to trace back your thought process, just to try and see if I've understood what you've done.
Sure.
Because it seems to me that actually the story is that there is a geometric rotational understanding of what I is. The traditional sort of archetype.
Yes, and this is always in our background as we
Yes.
try to perhaps talk about it in some other way.
Okay, but and you produced a different description, which is temporal.
That's correct.
And with those two descriptions, it starts to open things up.
I hope.
But it seems to, doesn't it?
Yes.
It
Right.
seems to.
Right.
Are there other descriptions, do you think, that could... I mean, this is opening up insights and making connections between things that we wouldn't necessarily have connected.
Well, right. So there might be, right? There might be other thoughts. The thought I'm having is that if you're looking for a generalization, then the generalization might be for everything spatial, there's also something temporal.
Yeah.
Or for everything temporal, there's also
Yes.
something spatial. And this is a theme that goes through and through mathematical physics, right? Like Einstein turned gravity into something highly geometrical,
Yeah.
but it's still temporal things going on.
Because when I first saw you do this, which was a few years ago now,
Right.
I was a bit uncomfortable because it felt as if you were sort of saying this is what time is.
Yeah, I certainly don't want to say that. That's why I'm prefacing this with the models are models.
Yeah, so I now understand it as this is an alternative description of the complex numbers.
That's correct.
Yeah.
Right. Or an alternative description of matrix algebra.
Yes.
Because, as we'll see. Okay, good. So now you see, I forgot. I got into a digression there. How are we doing in terms of temporality?
An hour and 10 minutes.
Right. Thank you. So what is the matrix model of all of this? Very simple. Here is the thing whose square is the identity. Right? And how are we going to make this match? Well, I'm going to say that an AB is a diagonal matrix. And then you see that what will happen if I take a diagonal matrix and I multiply it by a permutation matrix. That's important. So it's a little farther down the board, but if I take a diagonal matrix and I multiply it by a permutation matrix, then what do I get? I get the permutation matrix with the diagonal in the standard order, top to bottom, don't I? Right? A's are A and it would be B. Everybody knows how to multiply matrices, part of your arithmetic. If you put it in the opposite order, it will come out in the opposite way. That is, if I take 0, 1, 1, 0, and I multiplied it by, let me multiply it by something that's already in the opposite order, B, A. Sorry about that. It's hard to read when I write it incorrectly, but take that. So I multiplied it in the opposite order, I multiplied it by the guy in the opposite order on that side. And now I'll get the same result. That is, it flips it when I'm on the other side. So what happens? I'll multiply the matrices. 0, 1, nothing. A picks up an A, and 1, 0 picks up the 0, 1, and then 1, 0, sorry, 0, can't do arithmetic today. This is a 0, if you recall how to multiply matrices. 0, 1 times that is 0. 0, 1 times this is A. Okay, good. 1, 0 times this is B, and 1, 0 times that is 0. And so you see it comes out AB, the same as this. These are equal. So you see that eta times BA is the same as AB times eta. Right. So putting it back in the other notation, it says that eta times BA is equal to AB times eta, which is what I was saying before. So this is just matrix algebra, if you are already familiar with matrix algebra. Or you could say that we have just reinvented matrix algebra. Okay?
Lou, can I just ask one question? Is the two-ness that comes out of the existence of I, they're the same one as we refer to as hyperbolic in relationships? You know, when you write, I'm thinking differential equations again, but is it the same two-ness? Because it's a two-ness in both cases, isn't it?
I is made. Are you referring to?
Well, the most familiar one
Let me just take it out of the way and get back to your question. Hyperbolic, certain things can, I mean, you know that complex numbers correspond to ordinary rotational things, cosine and sine. And then there is hyperbolic cosine and hyperbolic sine, and they correspond to two-dimensional Minkowski space. And is that what you're talking about?
When you write the differential equation, in the case of a multidimensional differential equation, if you have opposite signs in the simple cases, you'll get hyperbolic solutions, and that's a two-ness has been brought into it. You can't make a three-ness out of it, and I'm just wondering if it's exactly the same two-ness as the one you're talking about.
I'm not sure, but let me react by doing something, and you'll see, you can tell me after I've done it, whether I came anywhere near close. To continue what I was just saying, what happens if we take A plus BI in my form, right? So this would be, let's just do the translation. This is AA, that's the A, plus B times 1 minus 1 eta, right? That's what it would be translated into in this form, right? This is not the answer to your question because I'm going to flip something in a moment. But what matrix does that correspond to? That then corresponds matrix-wise to AA 0, 0 plus B times 1 minus 1, 0, 0 times 0, 1, 1, 0. Sorry for all the calculation, but we wanted to find out what I ended up being in this matrix form. And by the time I do the rest of it, I get 1 minus 1, 0. So this guy is I. And there again, you may be familiar with that. That's one way of representing I in matrices as a matrix 1, anti-diagonal 1 minus 1, 0. And there's the ambiguity again, the 1 minus 1 is anti-diagonal. And then, excuse me, I'll just write the end result then. The end result is we have A, B, and minus B is the representative for A plus BI in matrices, right? Yeah.
Can I just make a point that actually relates to the question about the hyperbolic versus the imaginary? So your I, once you go to the Clifford algebra, when you're looking at 2 by 2 matrix, is actually a 2-bit clock. It's an interleaving of your sequence of +1, -1, right? So that's in a sense a one-dimensional clock, plus minus, plus minus, plus minus.
Yeah.
So actually, look, if you would draw just 4 column vectors down the bottom, 1, 0, 0, 1, -1, 0, 0, -1. So if you look at those things, those are the four states, right? It's a two-bit clock in the sense that each of the components is either 0 plus or minus 1. The 0 says we're not active there. So it's the interleaving of the two of your plus minus 1 displaced by the other. And so that's why you have the two-dimensional form where the eigenvalue is actually plus or minus r. Two of them.
I mean, in speaking that way, the 90-degree rotation is in the notation in that you rotated this by 90 degrees to get over here.
Absolutely.
With a sign shift.
That's right. And if you start operating that thing on the column vector 1, 0, you have the four corners of the spiral, right, which are the four corners of the thing. And the hyperbolic.
I agree, but I wanted to try to get to something hyperbolic.
Right.
So I wanted you to look at, so this is complex numbers, right? Here, this is complex numbers.
Yes.
What if we were to look at the following kinds of matrices? A, B, B. Right?
Mm-hmm.
Well, then I have, this is of the form A plus B sigma, or sigma, oh, that's just eta, actually. A plus B, eta. Eta is our friend, 0, 1, 1, 0, whose square is equal to 1. And if you look, and sometimes people call those dual numbers or double numbers or something, but they're related in Minkowski space and they're related to hyperbolic things. Why? Because in Minkowski space, you have t plus x, well, you have t plus x times t minus x is the norm, right? It's t squared minus x squared, the speed of the 1. You have, I should have put it the other way around, x minus t, but you want this to be equal to 0 on the light color. So what kind of thing is going to give you that? If you take t plus x sigma, you can, I'm sorry if that's a flipped way of looking at Minkowski space for the net, I should put it on the t, but yeah, I'll keep it there because otherwise I'm writing too much. But suppose you take t plus x eta and you multiply it by t minus x eta, then you get exactly that. You get t squared minus x squared, right? When you take t plus I x times t minus I x, you get t squared plus x squared, and that's the rotational one. But when you take the guy, when you use the basic thing as squared 1 rather than squared minus 1, you land on the Minkowski metric. And this is satisfied by then you have hyperbolic sine and hyperbolic cosine in there. So flipping that sign takes you over to the Minkowski situation. Is that close to your notion?
It links them up. It hasn't clarified for me the same thing, but it's sort of an extension of the same thing.
Yeah.
Yeah, thank you.
Yeah.
So if there's all these interpretations of I and structures and everything, is there, what I'm asking is there like a minimal structure or representation of I that could act as like a hierarchical building block for all these other interpretations of structures? Or am I asking?
Well, I'm thinking of building things from the notion of a temporal sequence that's acted on by a flip or some more complex kind of permutation operator that corresponds to a time step.
So would that be the minimal?
So the thing that's in the back of my mind is just a time step, actually. And the fact that I'm using this little simple permutation for time or some more complicated permutation for time is just because I'm interested in periodic models. But I'm not quite automatic about building this all up, right? Like there are automatic ways to build all the integers by collecting sets in a certain way. I'm not automatically building everything.
I was just wondering if it's possible to kind of grow these structures out of your minimal interpretation.
Well, we can talk about you see, you're asking a question which is an interesting one, and it comes up like if I'm thinking of the quaternion, complex numbers, quaternions, Newtonians, and then after people figured that out, they said, well, what is the recursive process of generating these algebras? And Cayley and Dixon came up with the Cayley-Dixon formula, which takes you from one to the next, and breaks down immediately after the Octonians, right, into algebras that aren't as good as the previous ones, but there is a formula that takes you from here to there to there to there. Since I'm working in a somewhat more general way, and I'm going to in a moment get all of matrix algebra, I'm not thinking of it as a single-step process. But I hope it'll become clear as we go along.
Yeah. It strikes me, and I'd be interested to know what you. I mean, I'm thinking of Bilson's thing about multiple descriptions.
Yeah.
And that actually having multiple descriptions is a very powerful thing.
Right. I'm a great fan of multiple descriptions, and can probably be as confusing as anybody by doing too much jumping around among them. But you know, if you're not listening to a lecture and you do have a lot of different descriptions of something, and you contemplate one of them until you're satisfied, and then look at another one and see what it all leads to, that's really
so that's where this business of completeness becomes really interesting, isn't it?
Yeah.
Because the lack of completeness is an invitation to generate more descriptions.
That's right. That's right. So if you, okay, well, let's come on. Does that tell me I should take a break or not? I would like to continue talking and then we'll take a break. To a certain point, right? So here we are, and then here's a natural question that immediately comes up if you're willing to, if you want to go a little farther, right? What if I had something that was period 3, ABC, 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 and I want to play with that, right? And what kind of algebra should I get out of that? Well, the time step, not the full period. In the earlier case, the time step was just shift from AB to BA, right? That's a natural time step. But here, I could shift from ABC to BCA, and then I could do one more shift to CAB, and then I'm back to where I started, right? So I'm cyclically going through them, right? And that's exactly what happens if you look up here. ABC, then start here and you get BCA, and then here you get CAB. So that's one of the natural symmetries that would happen. If you have an n-fold periodic sequence, then you get the cyclic permutation mapping. And you'll get one cyclic permutation, then do it twice, then do it 3 times, do it n-1 times, and then when you do it n times, you're back to where you started. And it's just shifting along the sequence, so it's a time step. So a time step in a periodic process is an n-through of unity, like that, in the sense of a permutation. So how will that work out? Well, I hope this is readable. Might be a little hard to read. Let's see, where's the pointer? I'll just point this way. So then my basic operation is shift the s across into just one time step, which means that it takes the z over and shoves x and y that way, okay? And now I have s squared, and that will take us twice, so move the x twice and yz there. And then if we do s cubed, that t is s squared. If we do s cubed, we're back where we started. And so now we have these guys, A, B, C, D, E, F, and G, H, K, S and S squared. And we can multiply them in the same way that I did before. But what does it correspond to in matrix algebra? Well, it corresponds to 3 by 3 matrices precisely, where the way to do it, I could say more, but the way to do it is you take this one and it's the diagonal. And then the DEF is DEF, and the GHK is the other one, GHK, which may incite memories of calculating 3 by 3 determinants by those 3, which correspond to the permutations involved. But that's exactly what they correspond to. You see, the S as a permutation corresponds to the matrix I'll say it rather than writing it out. If you took this matrix pattern here and you put in just ones where the S's are and zeros for everybody else, you get a little matrix which is a permutation matrix which does what S does. It shifts the first coordinate by 1 to the second coordinate, it shifts the second coordinate to the third coordinate, and it shifts the third coordinate back to the first coordinate. So this placement of S does what S does, and the placement of T does what T does. And so if you play with it a little bit, you find out that this guy here is exactly 3 by 3 matrix algebra. Okay? And by the same token, you get n by n matrix algebra in one way by writing down one cyclic permutation and then all of its iterates, which will fill out the whole matrix with positions like that. And you can just use it to translate the periodic iterant algebra into matrix algebra. So this is one of the patterns. These are patterns of matrices that have a cyclic permutation in the background. Okay? I hope that's believable, and it's probably better than doing more calculation, but let's see. Now the theorem is not going to be readable, so I'm going to jump across the theorem to the illustration of how to get to this. Suppose you have a finite group. Here's a nice finite group, cyclic group of order 3. I'm going to tell you what to do, okay? I want these permutation matrices that will work for it. So what I do is I write the multiplication table of the group. This is the multiplication table for that group. You should read 1s, s squared, 1s, s squared. 1 times anybody is the things in order. S times anybody, s, s squared, s cubed is 1. S squared times anybody, s squared, 1, s. Right? So there's the multiplication table. Multiplication table is almost what I want, but not quite. What I do is then permute the rows in the unique way that will put the ones on the diagonal. And now the elements of the group occupy multiple places in the matrix, and they correspond precisely to permutation matrices that do what the elements of the group are supposed to do. This is a matrix version of Cayley's theorem, which you learned long ago maybe, which says that every finite group can be represented as a permutation group. And it's a matrix version of it. Every finite group can be represented as a group generated by some permutation matrices, permuting the number of things that are in the group. Okay? So this is just a digression into a little bit about matrices. And in this case, it gives us back what I was just showing you, but let's look at something more complicated. Up here I have the symmetric group on, I didn't mean that. What am I saying? That's too bad. And that survived all the way into the published paper. What's wrong with this? I meant the symmetric group on 3 letters, which has order 6. But I wrote the symmetric group on 6 letters, which would be much larger, okay? So the symmetric group on 3 letters has order 6, and it's generated by symmetries of a triangle, for example, right? Where here's a triangle. Well, just to imagine a triangle. And you have a triangle, and it has 3 things, 3 vertices. And if you turn it, you get a cyclic rotation of the triangle. You can also turn it in such a way that you leave one of the vertices fixed and interchange these 2. Those are order 2 things. That's what I call F up there. So I have a rotation of the triangle and a flip. And now I have RF and R squared F and some relations. That if you do the flip and a rotation, it's the same as doing the rotation and the flip squared. Okay? So that's a symmetric group on 3 letters. It has 6 elements. Now, when I make a multiplication table, it's a 6 by 6 multiplication table, right? And there's the multiplication table. Here, this thing here. Like, for example, 1 times anybody here is that, there's the list. Multiply by r squared, 1, rf, r squared f, and f. You see what I mean? So I've written down the multiplication table, and then I permute it until all the 1s are on the diagonal, and now every element of the group is now occupying some places in this table. For example, R. R is here, here, here. And it's also here, here, and
Next,
let's see. Here, 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 and here, and here. There they are. 3 R's down there and 3 R's up there. And if you were to just erase everybody and just write down 1s for the R's, you would have a permutation matrix on 6, which had order 3. And the upper one and the lower one both are turning by 3. And the flip and everybody. It's all there. It's all there as permutation matrices. And that means that if I wish, I can have the symmetric group acting on 6 things by those permutations, and have iterants of order 6, and play with them, and they turn out to be 6 by 6 matrix algebra, where the underlying permutations is the symmetric group on 3 letters. That's more complicated than I want to use, but I want to show you one that's simpler, of the same ilk. Oops. Now what?
You went into the normal.
There's going to be some way.
Use a keyboard, it might be easier to get back into the full screen view.
Maybe. No, do you know what to do when
Well, you go back into the full screen view as initially.
Well, I pushed a button which made it have
It's readable, it's not.
there.
No, you need to go into the full screen view. You have
Oh, I see what happened. I got out of full screen view.
View on
Okay. Thank you. Okay, there we go. Now, here's an easier one. And this is called the Klein-4 group. A squared, B squared, and C squared are 1, and AB and BA are C. Okay, and any product of any 2 of them is the 3rd one. All right? That's a cyclic group crossed a cyclic group, and it comes up a lot. All right? And if you take the multiplication table and rewrite it, you get this. And then you can see here, here's A and A and A and A, and when you take the square of the matrix, which only has 1s where the A's are and 0s everywhere else, you get the identity. And here's the C all the way down the diagonal. That's the C permutation. And the B permutation are these. Okay? So we can do 4 by 4 matrices using the Klein-4 group. And then you can, for example, make the quaternions on 4 by 4 matrices by taking these special sign sequences of 1s and defining I to be equal to alpha times that permutation, J is beta times this permutation, and K is gamma times that permutation. And then you have another iterant picture of the quaternions. Now, exactly how I got those signs right is a matter of checking against the quaternions to make sure it works. I won't bother you with it, okay? But the point is that there are lots and lots of situations where you have patterned matrices that come up. If I have a little time, I'll show you how to do SU3 this way, which needs more analysis. But then you can write them concisely in the iterant form, and it may be useful to you, maybe. This is another way of saying what happened with the quaternions. There are these sign sequences associated with certain permutations. And this is permuted with that, this is permuted with that. These two are permuted this way and that way, and so on. So these diagrams represent the permutations. And when you multiply, you put the diagrams together, and then you follow back up to see who gets multiplied by whom. Because you see, this guy got permuted by the permutation. So this plus went over here, and this plus went over there. Nothing happened because of the way it was. they're symmetric. But they went up there and multiplied, and then the permutations multiplied each other, and you end up with the result. So that's a way of thinking about it. In general, that's the way the iterant multiplication is working. There's a permutation and some vector, and they're being combined like that. This is just a favorite matrix of mine, which we could analyze in a similar way if we wanted to. A Hermitian matrix which represents space-time, point, t plus x, t minus x, y minus iz, and y plus iz. Right? Has the right determinant, t squared minus x squared minus y squared minus z squared. Right? Good matrix to think about. End of algebraic digression. Where are we going now? In the slideshow, I went back to the Majoranas, but we could do that, but I want to skip forward to talk about the Schrodinger equation and then take a break. So pardon me while I do that. Okay, so what I want to show you in this section is how we can think of Schrodinger's equation, and the I can be thought of in both ways, right? The I can be thought of as the usual I squared I of the geometric I or the formal I, but it can also be thought of as an oscillation between plus and 1, plus 1 and minus 1. So how are we going to do that? Well, I'm going to begin by reminding you about the diffusion equation for Brownian motion. So Brownian motion is this, that x at time t plus tau is x at time t plus or minus some spatial shift, okay? Fixed spatial shift, and we're assuming that it's 50-50 probability to step to the right or step to the left. So then I wish to have the probability of being at the point x at time t plus tau. So what's the probability? Well, it's one. It has a half chance of coming from the left, and it has a half chance of coming from the right at the previous time. That's its situation. So the probability of being at x at t plus tau is the probability of being at x minus delta and the probability of being at x plus delta, each divided by 2. Okay? And that is the description for the probability for Brownian motion, but if you play around with it, it becomes a discrete differential equation, see? Because I can look at the probability of x at t plus tau minus the probability of x, and divide by tau, and that's a derivative, partial derivative with respect to time, discrete. And on the other hand, this is equal to, looks like I'm missing something. Yes. All right, so there's a mistake in this, but let's correct it. I have put in here this and that, right? And then I subtracted 2p of xt, and there's a 2 here, so if you divided that by 2, I would have subtracted p of xt divided by tau, so that's fine. And the tau is out here, but then this should have been delta squared, and this should have been delta squared underneath. No, everything is fine except this should have been delta squared. I see what happened there. All right. So h squared should have been delta squared, and then we're good. Okay? Everybody clear on this? This is supposed to cancel that. The tau we divided by, and the 2 is out here, so everything is just fine, but the h should have been a delta squared. Delta squared rather than h squared. Okay?
Yeah.
And now what are you looking at? You're looking at delta squared over tau here, and this is the second derivative. That's what that is. That's the second difference. So that's the second partial with respect to x of p. So this looks like this differential equation. Partial of p with respect to time is a constant times the second partial of p with respect to x squared. And the constant is delta squared over 2 tau. Okay? That's a diffusion equation, and it shows you that if you had a Brownian process, and if this ratio, delta squared over tau, was constant, and you let tau and delta both get very small, then it would in the limit look like this differential equation, diffusion equation. And then we know that this looks like Schrodinger's equation without the I, right? Because Schrodinger's equation, when you put in the momentum, looks like, Schrodinger's equation is this, and if you let the potential be 0 and take the usual formula for the momentum and take the square of it, you end up with the second derivative. You know this, so I won't go bothering that. But Schrodinger's equation in that form looks like d psi dt is I h bar over 2m d squared psi dx squared. H bar over 2m has the units of delta squared over time, distance squared over time. So, so Schrodinger's equation and the diffusion equation differ by an I. An interesting thing to puzzle about, right? So let's play with it. What would happen if I took the, what would happen if I did this? If I took psi at x at t plus tau equals I over 2 times this funny thing here. I just pulled it out of a hat, but it looks similar to the one I had before. Right? And where am I getting it? I'm getting it from here. Look at the difference equation that it corresponds to. So if I were to do this difference equation trick to this one, I would get this. The delta's in the right place now. I would have psi of x at this difference, same as before, and I put an I in there. So this is exactly the same as the one that we had before for the diffusion equation. I should have started here to make the slide intelligible. This is just the diffusion equation, discrete version, for the probability, but now I put an I in there and left it there for a moment, okay? So I have the I in there, and then I throw stuff away and pull this back out, and I get that recursion. So it says that psi at x and t plus tau would be, and now I have complex numbers in the recursion. And you could think of those, if you're thinking in terms of ordinary quantum terms, as the probability amplitudes for this process to jump or not jump or stay where it is. And, but then you'd be using the usual notions of quantity. Okay? But so far so good. I'm just playing with the equations. What would happen if instead I replaced the I here by -1 changing every time time changes? All right? So now the complex numbers have disappeared, and I have an alternating plus or minus 1 in this little stochastic process. And it's no longer interpreted as probability. I don't know what it is. It's some measure of the situation, right? Because I've mixed the Brownian process with this alternation, right? So every time you have the Brownian process, you have the ordinary probability calculation, except that every other time it's got a minus sign in front of it. And I don't interpret negative probability as probability yet. I don't know how to interpret it, but I just put in the minus sign. And then it will all work out and give me a -1 to the n of t there, right? And so I will have d psi dt is plus or minus times the second derivative. The plus or minus depends on the time. If time is even, it will be plus. If time is odd, it will be minus. The n of t is the number of, is the parity of the time step, which is assumed given, right? You can tell me if I, for a given time, discrete time, whether it's plus or it's minus, okay? Okay. Well then, how could we take the limit? This would be Schrodinger's equation, except that but how will it be Schrodinger's equation, right? It's a process, it's a real process, but it has this parity in it, plus at some times minus, at other times the signs are in there. Well, the only way to make the comparison is to separate the discrete things into those that have even parity and those that have odd parity, and then we can work with it. And what will that look like? That'll look like this. Now, at even parity, it will multiply by plus, and at odd parity, it will multiply by minus. And this will be at the discrete stage or in the limit, because I can let psi even mean the limit of the ones that have even parity, and psi odd be the ones that have the limit of the ones that have odd parity. There's no limit for the whole process. The whole process is oscillating between two things. But if you take the even things, then there will be a limit, presumably, and we can call it psi even. And then for the odd things, there'll be a limit, we can call that one psi odd. And now you see Schrodinger's equation has emerged, because I have two things, psi e and psi odd, and they satisfy this linked differential equation. So if I define psi to be psi even plus I psi odd, then just from this, we get Schrodinger's equation. I d by dt psi is I d by dt psi even plus I psi odd. And do it, and you get I, and I squared is minus 1, and over here, and out, and it works. Okay? So you see that we can, if we want to, think of the I in Schrodinger's equation as corresponding to the right symbolic thing to take care of the psi even and the psi odd as two things that are linked differentially. But in back of that, there is this stochastic process which involves the iterant, the actual iterant of plus and minus 1 in the background for the discrete process in back. So there's this clock running in the back which is multiplying plus, minus, plus, minus, plus, minus all the time. So that's a mathematical construction, but maybe it's worth thinking about it from a physical point of view.
You don't quite mean stochastic there, do you? Is it?
Something stochastic there. I don't know what's probably, I don't know how, all right, I shouldn't have even used the word. We know what the standard interpretation of probability is for quantum mechanics. So the question is, what happened? I started with the diffusion process, which involved probability, and then I decided to take that and perturb it mathematically, and I end up with something which satisfies Schrodinger's equation by means of this iterant to formalism conversion and keeping track of parity. At the end of all that, I have this differential equation which we interpret probabilistically in a different way. And I'm not sure what the relationship is between the end result of interpreting it probabilistically and the original result of interpreting it probabilistically. And should you think of it as a stochastic process in the middle? And Garrett looks like he has the answer to the question.
Actually, can I just make a comment, which does have a little bit of propaganda to it? We were talking about the hyperbolic and the trig functions and the number of states. My comment was you've got a 2-bit clock. The reason it's 2-bit, if you look at the two equations up there, they switch.
Yes.
If you back up one stage and say, go back to the diffusion equation and say, we're going to track 4 steps. And so we're going to have a 4-component memory of the diffusion.
Yes.
Then you can run that just like diffusion and then say, okay, let's do a transformation to change the coordinate system. And what happens is you can actually project onto 2 different eigenspaces. One eigenspace gives you precisely that, which is the Schrodinger equation, which switches back and forth. The other one projects onto the probabilistic a manifold where everything behaves as you expect probability to do. So your clock in the classical sense is a decaying exponential as opposed to a rotating exponential.
Yeah.
So you have two eigenspaces, they're orthogonal, and they have a different eigenvalue associated with them. So in the probabilistic sense, if that's where you're looking, that dominates. And the Schrodinger equation is then sitting in an eigenspace that actually has zero measure in the continuum limit. You don't go to the continuum limit, which in the end, of course, you don't have to because relativity says there's a limit. So that's where that comes from. It sits precisely with the hyperbolic. And so you have a four-state process that goes down to the 2x2, the 2-bit clock. The other 2-bit clock is classical. One component dies away, and so you just have a decaying.
Well, I think we should talk about this offline. We agree on the point. The point is this: seems to be something very rich going on at the discrete level.
Absolutely.
That is being beautifully ignored at the limit level.
Yeah.
And you see how it gets ignored by my need to assign parity to one, parity to the other, and work the symbolism. So then you can work at the continuum level, but there's more nitty-gritty happening in the discrete level here that also understood. Okay. So let's see where we are. We're at the stage where if you have the energy, I'll do 10 more minutes and quit rather than worry about a break. Is that all right? Okay. So that's Schrodinger. I'm not going to do the braiding of the Majorana fermions, but I want to go on and talk about Dirac. So Dirac is fun to think about. I'm doing this in a more or less standard way, but trying to interface it with both Peter's point of view and the algebra point of view that I've been using today. So we'll assume that the speed of light is 1 and the Planck's constant is 1, so that the relativistic relationship between energy and momentum and mass is just the Pythagorean relationship. E squared is p squared plus m squared. And we'll recall that Dirac wanted to find a square root for the energy, really for the energy operator, but I've written it as E here. So I'm going to write E as alpha p plus beta m and attempt to get E squared correctly. So you square it, and you find that you get alpha squared p squared plus beta squared m squared plus bm times alpha beta plus beta alpha. And then you realize, aha, there's our Clifford algebra again. If we use that little Clifford algebra with alpha squared and beta squared 1, and alpha and beta anti-commuting, why then it'll work. So then you can then write down a differential equation. I'm doing this with one space, one time, and then we'll generalize. So in one space, one time, I want that the energy operator is I times d by dt, and I want that the momentum operator is minus I d by dx. So that says that energy is equal to minus I d by dx alpha, that's in momentum, and beta m psi. So there's the Dirac equation, and the Dirac operator is what I get by putting everybody on the left-hand side. It changes a couple of signs, and so the Dirac equation is O applied to psi is equal to 0. So that's Dirac's beautiful notion of getting an equation. And here's a way to get a solution. I take a plane wave and I apply the operator to it. Now the plane wave is e to the I px minus et. And I apply the operator to it, and the operator has the property. We should just remember what the operator does. The operator is set up so that on the plane wave, the energy will pull down, the energy operator pulls down the energy as an eigenvalue, and that the momentum operator pulls down the momentum as an eigenvalue, but that's the minus one, so this will pull down minus p, and that will just multiply. So that's what happens. It pulls down minus p, and it pulls down m. And so we get that factor multiplying the plane wave. Okay. But now notice the following, that if I take the conjugate of this in the sense of this algebra, switching these two signs and multiply, then we get Einstein's equation again. These guys anti-commute, and if you just multiply this out, all the cross terms vanish, and you're just left with this times this times that, and this times that, which gives you e squared minus p squared minus m squared, 0, okay? So that shows you that if you take this guy with plus signs, it will satisfy the Dirac equation, because when you apply the Dirac operator, you'll get the other one, and they multiply and give you 0, okay? So that's a way to solve the Dirac equation from a plane wave. Now, that is essentially the same as Peter's nilpotent approach. Watch. We have this, that this comes out when you apply the operator, and I'll call this delta. And now notice what happens if I take this delta, this bit of algebra here, and multiply it by beta alpha. And I get beta alpha e, all right, and here I get minus alpha beta alpha, which is beta alpha squared, which is just beta, and here I get beta squared alpha, which is just minus alpha. All right, you could have multiplied it by something else on the left, and it would be the same. But the point is that now you have this u, which isn't really essentially different from this, it's just an algebraic shift from this. But instead of multiplying by a conjugate and vanishing, it multiplies by itself and vanishes. It's nilpotent. Just look at what happens when you multiply it by itself. This will square, but this is a square root of minus 1, remember? It's a product of two Clifford algebra generators. Minus e squared. This squares and gives you plus, and this squares and gives you plus, and the cross terms all vanish because of anti-commuting. Very important that all of these anti-commute with one another, so the cross terms all vanish. And there's the nilpotent. So that's the nilpotent, and this is exactly the same idea that Peter's using. What I hadn't noticed before was that you can think of it without the nilpotent if you wish to, but the nilpotent is really important, that it turns out to be the nilpotent. We can then reformulate as Peter does, here's the nilpotent, and just shift the operator if you like, or multiply things in the right way, and you get a solution to the Dirac equation from using the nilpotent. So it's essentially the fact that u squared is equal to 0, so when you apply the Dirac operator once, you get u, if you shift the Dirac operator a little bit, and when you apply it again, you multiply by u again, and it goes away. But why is the nilpotent important? Well, I think Peter could say more than I'm saying about why the nilpotent is important, but here you see, at least from the point of view of the things that we've talked about, that this is, and this again is one of Peter's points, that once you have the nilpotent, then you have the operator that creates and destroys the fermion. You think of the fermion as being created by multiplying by u, and you think of it as being destroyed by multiplying by u. So you have the creation and annihilation operators for the fermion right there in your hand from the Dirac equation, not by some fiat. And so if we were to tell the story again, and it's unfortunate that I decided to tell the story again, this is the same story, I just changed notation here. But if I shift the Dirac operator a little bit, and maybe that's why I was doing this, let me see. Yeah, all right, so I was being careful in shifting the Dirac operator so it gets multiplied by beta alpha, and then it will happen that the Dirac operator gives you u, and when you do it again, it gives you u squared. Okay, so that's what one wants. And then you would like the u dagger which corresponds to shifting time. So you're going to shift the thing in an appropriate way, and I'm just going to go quickly. So you end up with U, and you end up with a U dagger. And they have the right properties. They both square to 0, and they will have the commutation relations that work. And you get the algebra for the fermion coming out of the Dirac equation directly. And Peter details all, I'm just doing this in standard notation because I'm working my way up from standard Clifford algebra instead of going through quaternions. But it's the same beautiful idea. And I think that one of the significant things about this is exactly that the creation and annihilation operators for the fermion are coming out of the Dirac equation directly, and other properties of fermions coming out directly. So you can do the algebra, and you can find the underlying Clifford algebra elements as well, and so on. And it's very beautiful and I think very significant. So I won't go into the rest of this algebra here, because what I wanted to do is talk about the problem of what happens when we do it in 3 dimensions of space and 1 dimension of time. Now, if we go through exactly the same thing as we did before, then you have to put in more algebra because you have more p's. And one way to do that is the same thing, the same story that we've heard from Peter many times, which is that you double the algebra. So we started with a certain Clifford algebra, or we could have used the quaternions, but you want another copy of them to label the p's. You've got 3 p's, and you'd like to label them. So you label them with another copy of the algebra that commutes with the first one, and do everything I did before, and it all will work. And everything works nicely. I've written it here, but there's no point in going through it. The story I wanted to talk to you about is another one, which is what are you going to do if you want to follow Majorana's original idea, which was to write a Dirac equation which could have real solutions. And why did he do that? He did that because he wanted to do it just for its own sake, and also because he wanted to see if he could find a way to articulate a particle which was its own antiparticle. So its conjugate, the conjugates of things would be equal to themselves. So he wrote down, he went through the same algebraic process and wrote down a Dirac operator which could have real solutions. And to do this with this kind of algebra using epsilon and eta, you notice that I'm going to do this in this way. I'm going to have epsilon and eta without any i's in them. So we're in the split quaternions. This is one of the reasons for going back to that, because I want to talk about the Majorana picture. Majorana picture doesn't have I in it, and it doesn't have quaternions in it. It just has some real matrices in it, all right? And we can use these real matrices. And then I have a copy of this algebra, hats, these hats. And as you see, there are no i's in this differential equation. And the momentum part has some guys in it that are mixtures. This is the funny thing. Now, I can't go through why this, it's too late to go through why this gets chosen the way it does, but it works out to give the right algebra for E and P. It will. And these fellows are a mixture of the hatted algebra and the unhatted algebra. I don't know how to write this without a mixture the way you would in the usual case in order to keep things real. It's a little technical problem about not having to have an I in there in order to make things work. And it's a crossword puzzle that we could play with outside, but this is in fact one way to do it, which is equivalent to Majorana's way. So the question is, could you do the nilpotency with this? And I don't know how to do the nilpotency with this. In some sense, the nilpotency being as fundamental as it is, it ought to work here as well as it works elsewhere. but then I don't know how to do the algebra problem. But I was stumped for a while because I was hoping to just, for example, to write down a solution. Here in this text I'm explaining why it works the way it does, and we can skip that. But as far as getting a solution is concerned, we can use the previous conjugate method. I apply the Dirac operator that I invented here, and invented or reworked from Majorana, and I apply it not to a plane wave, but e to the px minus et without an I, and now we're working in the reals. And I apply it, and I get a certain factor times that, and then if I multiply it by its conjugate, then everything works fine. The Dirac algebra situation works fine, and this times this would be equal to 0 for the same reasons as before. And so we get a solution to the Dirac equation by multiplying this exponential by this bit of algebra, and you get a solution to the Dirac equation. So that's the substitute for doing it with a nilpotent and doing it with a thing times its conjugate. And as you see, with the Dirac equation, you're involved with the Clifford algebra somehow with the Majorana situation. You're involved with the Clifford algebra in some way that doesn't go away, and is a little different from what happens with the regular Dirac equation. So that's maybe not the most wonderful place to stop, because I stopped in a sort of tricky mathematical puzzle that I fell into, but I think that's where our time has brought us, and so I'll stop there and tell you that there are a lot of different mathematical pathways that one can explore with this point of view. One of the more interesting ones, which I'll show you later if you're interested, is taking SU3 and putting it in an appropriate basis, starting with the Kauffman matrices and writing it as iterants. And then after enough rewriting, it turns out to be very pretty looking that way, and maybe that will help in thinking about standard model. Stop there.
Thank you very much. I'd like to make a comment about the last thing. I mean, tomorrow, I've done it before, I'll show you I'll show the Dirac equation using your discrete differentiation. And that seems to have an operator which doesn't have a mass term.
Oh, yeah, I've thought about that before, but I haven't thought about it recently.
And
right.
if you look at that operator, there's no I in it. It doesn't need an I. It can have an I if it wants, or it doesn't have to have an I. And the thing is that
that's interesting.
if you look at that operator, it seems to me that that operator works for particle or antiparticle. So that could be the way into the Majorana constant. I'm not sure how, but it could be.
Yeah, we should look at that.
Yeah.
Comment. I don't think everybody realizes, but topological phase in Majorana fermions is the hottest topic in all of physics right now. Princeton is having a year of topological phase next year. It's just, it's not.
The discovery.
Yeah,
I'm sorry.
But okay.
No, I don't want to say.
That's right. That's because, remember I said that electrons appear mathematically as though there are two particles. And then if you have a long chain of electrons in a nanowire, you can actually try to measure the correlations at the ends of the chains. And people have been doing this and seeing that the mathematics is telling you the right story, that the electrons behave as though they were pairs of particles. Not pairs of particles you're ever going to separate out, but the interesting thing is that those particles have very nice braiding properties. Those particles that compose the electron, the little Majoranas, have very nice braiding properties. And so people are interested in that. They would like to control them, of course, but that's going to be very hard.
Unfortunately.
Yeah.
So we don't know if the electron fundamentally is a particle. It's only in it's solid state.
In some contexts,
Yeah.
the electrons are going to
Oh, yes.
behave that way.
Yeah, I mean, there are some things which don't seem to exist fundamentally, but which do exist in other contexts. For example, monopoles, magnetic
Yeah.
monopoles have been observed in solid state conditions, but not intrinsically. And so we don't know whether Majorana particles. I don't think there's any evidence the electrons are Majorana particle, but the one that could be is the neutrino.
Right.
We don't know.
The electron itself, of course, is not a Majorana
No.
particle, but this statement that it's composed of two particles, it's only in some contexts that it would be composed of two particles anyway, right?
Well, it's composed of four. It's got four in the Dirac spin, so there's no reason why it can't be split into two and two.
Yeah. But when the mathematics says it looks like it's made of these, the mathematics is telling you, I guess, that in some context you might be able to detect something that the mathematics is showing. Right.
Yeah, I was just considering what I said before, that the operator only has a differential in time and a differential in space. It doesn't have a mass term. The amplitude has a mass term, but the operator doesn't. So the operator could be represented. So that means that instead of four true variations, there's only two. When you've got a mass term, you've got 4 plus and minus variations. But if the operator doesn't have a mass term, there's only 2 variations.
Yeah.
And so you could put a minus in front, and it wouldn't make any difference. So that's we should have a look at that.
Yeah.
Any other questions or comments? Or have you been completely zapped by me?
Yes.
Well, I'm very interested in I mean, this is extraordinary, really. I just think, this reinterpretation of Peter's work, which I've only got to know recently. But have you got this? One of the things that really strikes me about Peter's work is this emphasis on symmetry, and particularly the sort of broken symmetry. Have you developed this interpretation as far as getting some sort of symmetrical patterns? And I'm sure you have.
I'm not sure of your question again.
Well,
Broken symmetry about what?
Well, broken symmetry both within physics and within nature. So obviously, Peter develops Fibonacci numbers out of his ideas of Nilpotent and Quaternion arithmetic.
Yeah.
Have you developed this kind of symmetrical? Is there something pictorial? I think.
I'm not quite sure what you're asking.
Okay.
Therefore, write it up on there. Mark.
Yeah.
So when
Sure. Use
for discussion on Thursday evening. See if anyone can come up with an idea.
Yes, excellent. All right. So that's yeah. I won't do it now. I'll have to think about it. Think about how
I mean, we could call this the end of the talk, and then we can keep on chatting.
I won't do it now. I'll have to think about it. Let me think about it.
Okay.
I was also thinking about some kind of movement thing. I mean, just the basic thing of the idea of this sort of tick-tock behind, underneath, because it's the whole idea of quantum being, the collapse of the quantum, so which is like the nilpotent as well. Now you see it, now you don't. Now it's here, now it's not. So there's something very, obviously very pleasing about that. About having that. I was just wondering, because the fact that there's various different things that have been going, it's all a bit like this at the moment. But because you're talking about the Brownian walk and the diffusion equation, and I was just wondering about the possibility. At one point you said steps to left, steps to right, and I was just thinking maybe there is something that one could do in that way that might, I don't know.
Well, I think what's important in this is, first of all, that there's this kind of distinction between, I mean, this is what you're going to talk about tomorrow, isn't it? This distinction between classical mechanics and quantum mechanics, and that this representation breaks that down. It actually, you start to see the thing as a whole. Then you have to look, well, okay, there's physics, the natural world, and then we have the social world.
The social world.
Yeah.
Yes.
Yeah.
Where are the distinctions there? And there is there is the distinction. There are the symmetries which you can identify in the natural world, and then we start to see Fibonacci patterns and all sorts of things in biology, the arts, everywhere.
Right.
Okay, so that's the pattern.
Fibonacci patterns is something that comes up with the braiding. I'll show you, but
Okay.
we don't want to do that now. But I wanted to mention something about symmetry in regard to your question, which might be relevant, and that is, think back to the Schrodinger equation, and we separated it into the real part and the imaginary part.
Yeah.
And then those parts are getting permuted
Yeah.
by the multiplication by I.
Yeah.
So there's this basic permutation, which is very simple, of flipping them around with regard to one another.
Yeah.
What happens with Dirac? Well, what happens with Dirac is this, that you're going to have 4 components, and here's the Dirac algebra, and these are real valued functions, okay? And that's what a solution to the Dirac equation is going to look like. It's in that algebra, in my form, right? And then this is acted on by these algebra elements and gets permuted around. It gets permuted around by the Klein foregroup with some signs.
Yeah. Okay.
Or by the quaternions with some signs,
Yeah.
depending on which way you're formulating it. So you have the action, and that action is like the time. The time isn't just a simple shift anymore. The time is this symmetry, if it's time at all. It's this symmetry of the way these functions are getting permuted around, right? By the Klein foregroup.
Yeah.
So you have four things in order, but they get permuted. They get permuted like this. These two flip, or these two flip, and those permutations are the symmetries that are in back of the iterant, which is ABCD, 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 ABCD. If you think about it that way, and then the Dirac equation becomes written as 4 equations, just like the Schrodinger equation is written as 2 equations, and the complex numbers are gone. But now it's like this, and there are these funny signs. You see, there's no algebra here at all. It's just these funny permutations that happen, and the momentum and operators. That's the Dirac equation that you're looking at there in those 4 equations. Just like you can split Schrodinger into 2 equations.
There's a well-known split of the Dirac equation into 2. But this is a split.
This is still 1 plus 1 I'm talking about. Right. Yeah. So what I started calling time turns into certain kinds of permutation actions on what looks like a temporal sequence. Could be a temporal sequence in the sense of that process, like the diffusion equation, next step, next step, next step, next step. And then it's getting permuted by these things. So it's a little strange, but maybe it's worth thinking about as a generalization of time.
One last question from Gon. I think he's itching to ask a question.
Actually, I'm sorry, it's a comment again, and it was somebody mentioned the idea of distinctions, and you might ask the question, well, look, we have this gorgeous theory, special relativity. You get it from very simple axioms. You call it a theory, and it is, and it works extremely well. But then you say, well, damn it, it misses quantum mechanics. How does it miss quantum mechanics if it's so good? And one answer to that is to say, well, okay, if you think about the world line of a particle, and then do a very primitive thing, say, let's say the world line of the particle has a scale, and that scale will just be denoted by a simple square wave that's plus or minus 1. If you start with that, if the plus or minus 1 is at the Compton frequency, you get the Dirac equation, and you see what the function of the plus or minus 1 is. And it comes back to this idea of a 2-bit clock. When you go over to the Clifford algebra, you've got the 2x2 matrix, and that clock, the clock that you tick around, when you drew that, the Argand diagram with the 1i minus 1 minus I,
right.
four corners of the square, there's a four-state process, and you can represent those with 2 bits, right? And the bits themselves are plus or minus 1. And when you look at that, you actually see this whole thing about the relationship between the complex numbers and the hyperbolic numbers. Just looking at the way that the clock actually works, when you put that out on axes with the 4-bit clock that revolves around, those 4 bits break down into 2 components: the cos and the sine, and the hyperbolic one goes to the cosh and the sinh, right? And when you then partition the differential equations, for example, the Dirac equation has the cos and the sine, it has the clock down at the constant length. If you put in the other clock, which is classical, you get the telegraph equations, which have a diffusive clock, right? The only measure of the time is through the ensemble, not through the world line itself. So, in a sense, what you have to do to extract quantum mechanics, at least simply in the 1 plus 1 dimensional case, is to convert the world line into this clock that just has the plus and minus 1. And because you need the 2 components, because if you think of special relativity in the world line, you put a point on the world line and say, what regions do you have to partition? What distinctions do you have to make? You have to make the distinction future, past, left and right. You need to do that to get to actually tell the time in that system. And it's those 2 bits, you put them together, and that's where you get the clocks from, and that's the reason that you have the 2 dimensions. And so it's a very simple picture.
Okay, no doubt you'll give us the details.
Tell me that slowly.
Will you give us the details when you give your talk? Are you going to give us the details when you give your talk?
Good.
Yeah.
Good.
Great. So, I look forward to that. Okay, thank you to this thing. Apparently, Peter Marshall's trying to Skype me, and he doesn't know that we're at an ANPA meeting, so I thought I would... some people know Peter Marshall from ANPA meetings, so I'm going to see if I can Skype him and get hold of him. Here he is. He was trying to Skype me about half an hour ago.